Hello, you beautiful people. Today is again a reaction with changing density, but we want to have a look at the plug flow reactor. So last time you got a worksheet, it was worksheet 3, where we talked about changing density in a continuously stirred tank reactor, and today it's the plug flow reactor. So a new worksheet. I put some slides here from the worksheet, and I just want to give you some explanations about what you should do at your homework. Okay, if you look at the plug flow reactor, so you have a volume flow at the inlet. If the density is changing, then the volume flow is not constant, but it will increase or decrease while flowing through the plug flow reactor. You have an inlet concentration of component A, and at the outlet you have your conversion. In the example we set it to be 80%. Okay, and if you now want to calculate what's happening inside this plug flow reactor, then you can take a very small slice. So we say this should be infinitesimal. So it's just having the volume dV. And so you have a mole flow of component A entering the reactor, and you have a reaction taking place inside this very small slice here of our plug flow reactor. And at the outlet you have a slightly changed mole flow of component A. So that's why we call it N dot A, the mole flow of component A, plus this very small change. Okay, and then you can go for your mole balance. You can say, okay, the mole flow going in minus the mole flow going out. This is this one, minus the reaction that takes place inside this very small slice of the plug flow reactor. This is the mole balance for this, and then you will see, okay, my mole flow A, this is you can cancel it out, so I can do it here for you. So this cancels out here, and then you can rearrange your then you can rearrange your equation, that you just say, okay, your change in the mole flow of component A, this is the reaction rate times the very small volume here. So, and then you have a governing equation, or you have a differential equation that you can try to solve. But for what we are doing here, so it's since we have a reaction with changing density, so it's more convenient to rewrite it with the conversion. So if you remember last time, you can say, okay, my mole flow at some point inside the plug flow reactor, this is the inlet mole flow. So you can also write it here, N dot A0. So this is here. And you can just calculate it by 1 minus the conversion of component A. Okay, and now we want to substitute our DNA here. We want to substitute it by the conversion. Okay, how can we do this? If you just write, okay, you want to have d dot Na over dxa, so you just calculate the derivative of this, then you will find, okay, so the first term here is a constant, so this skips out, and the last term, if you are calculating the derivative of n dot a0 minus x. So I think you know what I mean. So this is the same as n dot a0 minus xa. So if you do the derivative, then you will find, okay, this is just minus n dot a0. And then you can rewrite it. If you want to know DNA, this is minus n dot a0 times dxa. Okay, and this we can, or this I wrote here. And now we are just replacing this here on equation 4. So this is just building the derivative, then we can rewrite it like this, and then we can substitute it over there. Okay, and then this is the new equation that we get here. So now we can express it in terms of the inlet mole flow of component A, the conversion, the reaction rate, and the volume, or the dV, the infinitesimal volume. And by rearranging, this is just 1 over R, 1 over the reaction rate, times dxa. This is 1 over the mole flow times dV. Okay, and now it's just integration. So you just write your your integration here. So the reaction rate changes with the conversion. So you have to put this inside the integral. We start with no conversion at the beginning, and then we want to go for xa. And here our mole flow at the inlet is a constant value. That's why we can just put our integral here. We start with a volume of 0 at the beginning. So when you're just entering the reactor, you have no volume, and you integrate up to your end volume. Okay, this is what's here. And then if you just say, okay, I have 1 over n dot a times integral dv. This is the same as just the volume divided by the mole flow. And then we are just expanding it with our volume flow at the inlet. So our volume flow 0, and then we have V over the volume flow. This is just tau. So let me write it here. V over, this is tau, our residence time, and the other term is the volume flow divided by Na0. This is 1 over our concentration at the inlet. And this is what I just wrote here for you. So first you solve your integrals, and then you play around with the values that you get, and then you find, okay, the reaction volume divided by the mole flow at the inlet, this is just the same as the residence time divided by the concentration at the inlet. Okay, and then it's just rearranging. The main equation for the plug flow reactor is that the residence time is equal to the inlet concentration times integral 1 over the reaction rate, and then you integrate it by the conversion. Okay, and for R1, for R1, just in case it is a first order reaction, then you just put in your rate constant times your concentration, and then you can solve it for first order. Okay, so the calculations I want you to do is determine the required reaction volume if a constant density is assumed. So if, like we did it for the CSTR, first we calculate what would be the outcome if we say the volume doesn't change. Then we say, okay, it's changing, and you have this value for epsilon, the fractional change in density of 0.5. And then you should calculate the correct volume by solving the integral. So now you have to insert here your concentration A. Then you have to rewrite your concentration in terms of the conversion, and then you will hopefully get a result. And I think the integral that you should solve is not that easy. So you can go for the table of integrals, and this where here is written. So in the PDF file that I upload you an email, there's a link, so you can just click on here and then you will find a table of integrals and you can look for the right integral to solve this. Okay, for C, compare this volume to the size of the CSTR of worksheet 3. So maybe it's bigger, smaller, I don't know. Maybe you have already a first idea of the size comparison. And then part D is determine the required reaction volume by a numerical simulation. So again, it's the Euler scheme, including the effect of changing density, and compare it to the volume epsilon. Okay, what does it mean? So here in part B, you will do it analytical. So in part B, you will do this analytical. You know the integral that has to be solved, and then you can look it up, and then you get, just by calculating, you get the results. And in part D, I want you to do it numerically so that you can compare it. And maybe just a small reminder. We talked about the Euler scheme already, but there we had it for a batch system. So there we had the change in time, but now we want to have the change in volume flow. So it's a little bit different, but basically what you should do is that you take a slice like this, and then you can just say, okay, like we had it in your dn, for example, dna is the same as minus RA dV. Then you have to look for, okay, what does it mean for dnb? Or maybe it's better to not write this d, but to write delta. And you also have to ask yourself, what does it mean for component C? And then you can just say, okay, my n dot a new is n dot a old plus delta n dot a, and so on. Okay, but what's a little bit new here? Okay, so we are talking about the mole flows and we can calculate them, so this is no problem. But for our reaction rate, we need the concentration. For our reaction rate, we need RA is K times CA with CA should be the mole flow divided by the volume flow, and this is not constant since we have a changing density in this system. Okay, and at least what I did, maybe you can solve it in other ways, but at least what I did is that I said, okay, let's have a look. How can I calculate my conversion? My conversion is XA. This should be n dot A0 minus NA divided n dot NA. So you can calculate this for every slide of your reactor. So again, you have here, you have a slide and so on. Maybe this is I, this is I plus 1, this is I minus 1, and so on. And so you just, if you're right now, if you're in your slide I, then you can just calculate your mole flow in this slide. then you can calculate the conversion in here, and then you can say, okay, my new volume flow is the volume flow at the inlet times 1 plus epsilon times epsilon times XA. Okay, and so this means for every slide you have to update your mole flow, you have to update your conversion, you have to update your volume flow, and you have to update your concentration. And with the concentration you can update your reaction rate, and then so on. So basically this should be the idea for the Euler scheme, and with the Euler scheme it should be possible for you to hopefully get the same result as the analytical simulation. So this is the way how you can control yourself. Okay, it's also you have to find your choice of delta V. You have to consider, so if you would say, okay, let's say delta V should be 1 cubic meter, maybe this is too big. If you say it should be 1 liter, maybe this is too small. So you have to find a suitable choice of your delta V that you can calculate it here. And then you can do it with Excel or you can do it with MATLAB, but I will give you my solution will be MATLAB. Oops. My solution will be MATLAB. So if you want to compare the code, then maybe you can do it in MATLAB, but Excel will also be fine. Okay, then good luck for your simulation. And yes, I forgot about it. I will create a new online test and email, and it should be, deadline is Friday, May 8th. Okay, then have a nice week, and if you have any questions you can just email me or just contact me. Okay, bye.